Hello, my name is James O'Neill, and this is my project on artificial blood vessels. So, artificial blood vessels are medical devices used to replace damaged or diseased blood vessels. They improve the quality of life for patients with these cardiovascular conditions. And the blood vessel that was chosen for this project is the descending aorta. And this was chosen because it is the most common blood vessel to rupture and need replacing. For this project, we had to find the volume flow rate in the chosen artery, determine the appropriate size of the model, and as well as find three biocompatible materials with their material properties and their cost. So some history on artificial blood vessels. They've been in use since World War I. However, back then they were made out of glass and aluminum. But in 1940 and 1950s, they started being made out of synthetic fabrics such as polyethylene and silicone rubber, which are two materials that we still use today for artificial blood vessels. However, a main issue with those is that they were very prone to forming blood clots. But in the 80s, a scientist by the name of Donald Lyman was able to synthesize a polymer which improved the material's elasticity, which reduced the blood clot's form. And this leads us to where we are today, where scientists are bioengineering blood vessels that are able to incorporate living cells so it becomes a part of you instead of having a foreign substance in your body. The materials that I chose for this project are silicone rubber, polyurethane, and polyester resin. And below them are their material properties as well as their cost. And the reason I chose these materials is because they've all been tested in the past as artificial blood vessels, and they're all cheap and flexible. Here's the drawing for the 1 millimeter vessel, the 10 millimeter, and as well as the 100 millimeter. So here are the flow simulations that were done. To do them, I used the wizard tool in SolidWorks, and the initial design parameters where the fluid was changed to blood, the temperature was changed to 310 Kelvin, and the pressure to about 16,000 pascals. These temperatures and pressures were chosen because those are the average of human blood. And two initial boundary conditions were made. One was the inlet volume flow, and the other was the environment pressure. So you can see on the top is our initial volume flow, and the bottom is our 5 times the volume flow rate. But I don't know if you can see the numbers because they're quite small, but the pressure is the exact same on both of them. So changing the volume flow rate had no effect. And this could be due to the fact that the initial volume flow rate is very small. So increasing it 5 times just does nothing. And after the flow simulations, we ran a static simulation. And to do this, we fixed both faces of the vessel and then added an external pressure on the inside wall. And that pressure is the pressure that was calculated during the flow simulations. And with these static simulations, we're able to get the stress and the strain. Here is the data. So for the 1 millimeter, the silicone rubber had the lowest stress. But after that, for the 10 millimeter and the 100 millimeter, polyester resin is the one experiencing the least stress, and it had the least strain for all of the simulations. This leads us into our product recommendation. So again, I would choose polyester resin. It experiences the least amount of stress and the strain, and this could be due to the fact of it having the greatest elastic modulus. It is very cheap and easy to manufacture, and it costs about $1.50 to $2 per kilogram. And if we were to use the hoop stress formula to calculate the expected stress acting on the vessel, polyester resin had the closest value, so it has the lowest percent difference. And here are my sources. Thank you.